Well, here we are again. This is going to be part 2 of building a PLC trainer. There is another video on the PLC Professor YouTube channel with that same title, and I think it's called Part 1. And basically, this little project is extrapolated out of that project. It's going to use the same basic design, but we're going to max out the little box. So we're basically building the same trainer, but we're just adding more components. We're going to max out what you could do with that 10 IO point controller. Now, if you haven't watched the other video and you are an old hand at drilling holes, soldering wires to switches, etc., you can just start here. But if you're a relative novice, then you really should go back and watch the other video first, because in this video I do not repeat all of the same techniques and skill descriptions that you need to properly connect the conductors to the devices and to the controller. So if you're a novice or you're not sure, go back and watch part 1 first, then come back and watch this one. Actually, I think we'll call this Part 2a, maxing out the little box, because I believe that this is going to go more than 30 minutes to do the whole presentation. We're going to stop when we get past 30 minutes, and then we'll do Part 2b. With this one, we're going to start with a schematic. We're going to start with also a wiring diagram. If you look here, you see right in the middle of the screen a gray box that's labeled 1761-L10BXB. This is a model of an Allen Bradley programmable logic controller. This is the smallest processor available, the least expensive available in the Micrologics family. And that is the reason we started to use this model 6, 7, 8 years ago when we started working on these projects. This is limited to 10 IOs. So you see in the part number L10. If it were an L16, then you'd have 10 inputs and 6 outputs. But an L10 has 6 inputs and 4 outputs. And you can see the inputs here are broken up into 2 groups. The first 4 input points, 0 through 3, have their own DC common, and then there's a second group of 2 inputs that have their own DC common. However, we're using them all just as one group. And then for outputs, there are 3 groups. The first 2 outputs, 0 and 1, are isolated and can have their own commons, AC or DC. And those are relay outputs, by the way. So output word 0, bit 0, and bit 1, those bits of memory control relay outputs. And then the second 2 outputs are in one DC group. Now, I provided you this wiring diagram, and you'll notice that for the 6 inputs, the first one is diagrammed or designed a little different than the other 5. So there are some variations here. The last 2 inputs, even though they show the same as inputs 1, 2, and 3, in our little project here, those are going to be normally open only push buttons, where here I show a diagram for a push button that has normally open and normally closed, and then you connect up which of the 2 that you want. However, the only one that's really different is input 0, because we wired a normally closed in series with a normally open. So if you look at that electrically, right now the toggle switch, it's a single pole double throw, it is open. So if you push that push button over there, because it's normally closed, when you push it, it's going to go open. Well, it has no effect on the input. In this position right now for the push button, remember it's spring-loaded, normally closed, you can flip the toggle switch back and forth and turn input 0 on and off. Or you can turn the toggle switch on, in other words, flip it on, and then you can use the push button as a normally closed push button. So we wanted to provide you, and this is different, by the way. This is the one major difference. between this trainer and the one in the previous video. In the previous video, it was just 6 toggle switches. Here we have 6 toggle switches, but the first toggle switch is wired in series with a normally closed push button. The other 5 toggle switches are wired in parallel with push buttons. If you need a momentary input, say for input 2, the third one down, you just leave the toggle switch closed and you just push the push button anytime you want an input. And that's the reason for putting push buttons, normally open, in parallel with the toggle switch. The reason for wiring the first input, as we did, is to give you the benefit of having a normally closed push button to work with, or you can just work with the toggle switch as you did with the previous trainer. But there are a lot of instances where having a normally closed push button, meaning it's spring-loaded closed, so it's closed all the time until you push the button. A lot of people get confused between normally closed input device and a true if off instruction in the PLC. Now, if you don't, if that doesn't ring any bells, then you need to go watch the whole lecture series on PLCs. Nonetheless, those of you that are building a trainer, let's move on. Now, although I have provided a basic wiring diagram here for you, you are still responsible to download the installation manuals for the controller that you're going to use, even if it's an L10BXB. You need to download the information, verify all the proper wiring, and verify the voltages before you proceed. Matter of fact, you should verify what I've shown you here just as common professional practice. Okay, we're doing this a little bit different. In the other build a demo or build a hardware trainer videos, we started out a little bit different. Here I'm showing you the finished product, a Micrologix 1000 1761 L10BXB bolted down to the bottom of the black project box. This one I believe I bought at Radio Shack. I buy project boxes from All Electronics. I buy them from Jameco Electronics. I buy them from a lot of places. This one I believe I purchased at Radio Shack for $5 or $6. Can't remember the exact price. Anyway, so drilled 2 holes in the bottom. Now the untouched box to the right is the cover plate is face up. You see the 4 screw holes. But I'm actually flipping it over and bolting the PLC to what you might call the bottom of the project box. There's a good reason for doing that. Besides the 2 holes for the 440 hardware to bolt the PLC to the bottom of the box, there's also 2 holes that you see over on the left end, and that's for wires to be pushed up and run to the screw terminals on the PLC. And what you can't see is over on the right end of the box, there is a hole where we've mounted a DC power panel mount jack, which is also in the picture there. So we're showing you the components that you need to go out and purchase in addition to the finished project. The one thing we're not showing you is a PLC sitting there unbolted down and unwired up. But there's one in the picture. So you may not actually use this controller. You may want to use a different controller, but make sure that you buy a box that will accommodate the size of the controller, because this is one of the smallest. But the main components that you want to get first are those shown right in front of you in the front. 6 toggle switches, a power jack, DC power jack, and I'll just warn you that that power jack needs to match the dimensions of the plug on the wall wart, the 24-volt DC power adapter that you purchase. Now, if you purchase one with a wrong adapter, the wrong plug on it, you can cut it off and solder on the correct one, but it's a pain. So buy your 24-volt DC power adapter. Needs to be at least half an amp, 500 milliamps. Look to see what the dimensions are of the power jack. In this case, I use 5.5 millimeter by 2.1 millimeters. That's pretty much the standard that I used. So there we got 6 toggle switches. We have a power jack so you can plug in 24 volts DC. And then we have 2 push buttons with red caps on them. Those are just standard, normally open El Cheapo push buttons. I buy them mostly on eBay. Matter of fact, almost everything that you see here, other than the controller and the black box, I purchased that all on eBay. And then you see 4 lit or lighted push buttons. Now what you'll notice about those 4 push buttons is that there are 4 terminals on the back, 2 for the LED or 2 for the light, and then 3 for the single pole, double pole, well, single pole, normally open, normally closed, or Form C contact for the push button. A little closer look. There's not much more to see there other than a real good correlation between where the components go on the face of the box and the components, what they look like. Now, one thing I will point out, that all of these components, except for 2, and I see the DC power jack is out of view in this photo, my apologies, but most of these components insert into the drilled hole or the bore from the back, from the inside the box. The lights go in from the front and the nut goes on the back. And we'll point out later some problems with that. Here's our 6 toggle switches, our 2 push buttons, and our DC power jack adapter, panel mount, bulkhead mount. When you go looking for these things on eBay, they refer to them as panel mount or bulkhead. The center pin is normally positive. Anyway, looking at these toggle switches, with the toggle switch in this position, when you consider the common pin on the toggle switch, with the toggle in that position, it's going to close this side of the toggle switch. So the center pin, which is common to both of the 2 outer pins, the center pin will be connected to the pin on the left when the toggle is to the right. So if you could see how it was built inside, you would see that the 2 pins that are connected are on the opposite side as the direction of the toggle. The only reason I mention this is so when you wire up your toggle switches, you may want to mount them so the toggle is down, off, and up, on. That's a convention, not necessary. Then you see in the upper right-hand corner kind of the symbol that we're going to use. And you see you have a common connector, common conductor, and then you have a switch lever that can be moved, toggled back and forth between 2 connections. We only show 1 connected here. We don't show the second one connected because in this case you're only going to use 1 set of contacts. Now you could purchase single pole, single throw toggle switches, then you don't have to concern yourself with which terminal is which. These switches have no polarity, but you definitely have to have one of your conductors on the middle pin. Another thing that I would like you to notice is how shiny the solder terminals or lugs are on these switches. That means that they're ready to accept solder. If you get toggle switches that have darkened or dirty or corroded solder lugs, you may end up applying so much heat trying to get them to burn off the dirt before they accept the solder that the heat will go into that black plastic body and actually start melting it. The pin becomes loose and you ruin the toggle switch. So you want to be really careful when you're soldering wires to these. You want to make sure that they're well cleaned first. If you want to hedge your bets, in other words, guarantee success, then you're going to want to go to the hardware store or to a place that sells electronics components, that is, solder, and buy some solder paste. And you put a little dab of solder paste on each of these pins, these terminals, and then you apply heat until the solder paste melts. At that point, when you go to solder then, because you already have flux on the pin, it's going to clean up all the oxidation and the solder will wet to the surface very quickly. Okay, we also have push buttons here, and these push buttons are just straight normally open push buttons. There's not a third pin, so you do not have to concern yourself with normally open, normally closed. And then there are two connections on the DC adapter. The one you can just barely see in the center, and the other one is the ground or the negative side. And typically the center pin is positive, and the center pin goes straight through to the back. So if you're following conventional color coding, red for positive, black for negative, your red wire would be soldered to the middle connection and your black wire to that long tab that's hanging out from the outer shell of the body of this device. Be warned that there is plastic insulation between the center pin and the outer housing. If you apply too much heat to that center pin, it will melt the plastic and it will dislodge that center pin. It may move a little sideways, or you might push it right out the front. So be very careful when you're soldering up these devices. Okay, another point on the toggle switches, there are 4 removable pieces of hardware, and they come off in the order shown. To the far right you see a nut, then a lock washer, and then a locking tab washer. Then of course you see the toggle switch with a nut threaded on all the way to the base of the threaded shank or shaft. Typically I leave that nut on and tighten it down against the body. Now you don't want to leave it loose. You want to, and when I say tighten down, I mean snug, not tight. And I use that as a spacer primarily because the thickness of the plastic of the box doesn't need that many threads showing, and the more you have hanging out, the less attractive it is. So the nut I leave on there and I snug it down. And then this locking tab washer, notice that there are 2 tabs. There's a little tip there in the inner diameter, and then there's a rolled over tab on the outer diameter. The one on the inner diameter actually slides in a slot on the threads. Now if you look at the threads to the left there, going down in the shadow, you see a dark line. That little tab slides down in there. That way the switch is held in position with this washer. Then that other tab that is rolled out perpendicular from the washer, sometimes people drill a little tiny hole in the face of their panel or their box, and when you slide this on, that tab engages the surface of the box. So the outside tab grabs the box, the inside tab holds the switch. That way when you lock this down, the switch itself can't rotate. Now I don't do that. I typically use that washer anyway, but I put the perpendicular tab, the outside one, facing out. I just use it as a washer. And then of course you have a locking washer, and there's several ways you can use that. I typically use it to lock that locking washer to the plastic, and then I put the nut on the outside. Then of course there's your star washer, and you can't see it very well, but those little tabs that stick inside of the inside radius, they are actually twisted. If you look at one of those, you'll see it's a little twisted. Those teeth grab into either metal or plastic, and it's a lock wash. And then of course you got the outer nut. Okay, now looking at the back of our combination push button light. It's a lighted push button. That does not mean that the push button and the light are connected together, because they are not. They're 2 separate devices in the same housing. And that is exactly why I use this type. There's another type that you cannot separate them. In other words, it's internally wired, so when you push the button, the light comes on and the switch closes or the switch opens. We don't want that. In other words, these are push buttons to go in parallel with the toggle switches, and they're also for the outputs. So we have a common. You see in the middle of the base there, it says C for common. Then you have a normally open, NO, and a normally closed. This is a Form C contact. And this is the symbol that we used in our diagram. And then, of course, we have the output light. We have a positive and a negative terminal. Remember that we're using DC outputs. Now, the reason we're using DC outputs is because we want to use LEDs. Now, for a solenoid valve, if you want to use 24 volts AC instead of 24 volts DC, more power to you. But in our little example here, folks, we're using blue lights. Matter of fact, it doesn't matter what color the lights are. One thing I will mention, that these particular, and these are the only 4 that I had like this, and they're the only 4 that I had at the time I made this project, they're actually 12 volt DC lamps. So I had to add 180 volts, 1/2 watt resistance in series with these 2 terminals, not across them, but anywhere in series to drop the 24 volts down to 12 volts. You won't have to do that because you're going to buy 24 volt DC lights. Okay, remember I told you that we're not going to go over everything that we went through in the first project video. So here we're back and we've got the holes drilled. I will have to say that the big holes didn't go very neatly. You can see some little burrs there. I didn't have the correct size bit, so I had to use a Dremel tool to enlarge the holes to the size I needed for those lit push buttons. Now I have the right size bit. So it's still going to come out fine. And you can see the scratch marks or the scores where I scored the box to mark the positions for to drill the holes. And I typically drill with something like 1/16 of an inch bit. So I would drill all 6 holes, all 12 holes. Well, actually, there's 12 you can see here. There's 1 on the end. That's 13. And there's 2, 3, 4 on the top. So there's a whole bunch of holes. I drill them all with a 1/16 of an inch. Being very careful to get it right in the crosshairs of the 2 scores. Then I use an 1/8 inch bit, and then I work my way out to 1/4 of an inch for the 6 toggle switches. The 2 red push buttons, I think they were a slightly larger bore, and then of course the lit or lighted push buttons were much larger. It seems like they were 9/16 of an inch. So, you know, most drill indexes go to a 1/2 inch. So you would have to go out and purchase. Now, there's another way to do it, and that's to get one of those multi-bits or Vera-bits that has steps in it. And you just keep pushing it in until the hole gets the size you want, and you're done. So, double check the required bore size before you grab your drill and start making holes in your box. Now, the box was only $5 or $6, so if you run it, don't get all wrapped around the axle about it. Go out and buy another one. I mean, you're going to have, you know, $150 or more into your little project here. Why end up with something that doesn't look good for the sake of a $5, $6 box? If you had to wreck 2 of these getting one right, fine. Now, you see that circle template laying in the background there. That was kind of a leftover from way back when. And I didn't throw them away because occasionally when I'm flying or I'm stuck in an office somewhere waiting, if I have one of these in my briefcase or in my laptop bag and I want to do some sketching, because I like to make neat sketches. I don't like just scribble up stuff. I kept this. However, it also works out very well for taking your devices and fitting them to see which hole they fit in the best. That way you don't have to hold up the threaded shank next to your drill bit and try to see if that's too big or too small. So having one of those circular templates is not a bad idea. Don't go out and buy one, but if you've got one, you're in good shape. Okay, so then we're going to mount the switches through the outside of the box. Now, this is not where these switches are going to go when you're finished, but we're putting them into these holes from the outside and tightening down the nut. We didn't put on the lock washer and the locking tabbed washer, just a nut to hold them in this position so we can do some soldering. So you don't have to tighten them down real tight, but make them snug and make sure your switches are nicely aligned with each other before you start. Okay. Now you're going to measure with a ruler, yardstick, tape measure, whatever you have, the distance from the center solder lug on one switch on one end to all the way to the other end, because we're going to need a piece of conductor stripped to that length plus a ½ inch. We need a little to spare. So then now we're going to strip the common positive wire. Now I'm using red wire for positive. It's a good idea. Notice that I did it in small pieces. I didn't try to strip the whole 6 inches or whatever it was all in one go, because you may actually break some conductors. I did it with an inch, inch and a half, 2 inches at a time. Then you're going to take, and by the way, it doesn't come out of the insulation all nice and tightly twisted together like that. What you need to do is let the red wire dangle down between your legs. Hold the red insulation end you see right there between your thumb and forefinger, and then grab the conductor, the copper strands right above where the plastic is, and then start twisting the red plastic while you move your fingers up the length of the copper strands. So that what that allows you to do is to twist it fairly tight, and when you're done, twist it, make sure it's nice and snug, and make sure it's straight like you see here. It doesn't have to be perfect, but it should be pretty straight. Okay, then you're going to tin the common red wire, and to do that, and this is not a very good picture, but it's close enough for the folks I hang out with. Anyway, you're going to put some solder on the tip of your soldering pencil or soldering iron, lay the stranded or the stripped section over as you see right here, and then place solder right where the two touch, and then keep feeding solder into the solder pool, the melted pool, as you slide that strip of stripped copper twisted together all the way to the end until the whole thing is nice and soldered. Okay, here you see it nice and soldered. However, we're also to the next step. So notice what I've done. To the far left, you see that the unsoldered or the stripped stranded copper is on top of that tab, and then it swings down and comes up against. So it's above there. It's above there, and it's below there. So we basically have the wire, the stripped tin conductor. This is going to be our positive common. We have it wedged, if that's the right word, in between the two end terminals. Now we're going to solder first the one on the right. We're going to solder that one first because we've got physical pressure of that conductor against that pin. Now remember that the pins are already supposed to be clean and ready to accept solder. So when you put your soldering tip up against those two items, the tin common and the solder lug, within a second you want to start flowing solder into that joint. But don't leave the soldering iron or pencil against there too long, otherwise you'll damage the body of the switch. You'll have to pull out that switch and use a different one. Okay, now you see that connection is soldered. Now there's a little dirt on the joint, but it's still a good joint. What makes a good solder joint is that you have a concave surface, meaning that the solder is well wetted to the soldering lug and well wetted to the common conductor that we're using. Now since the common conductor is already tinned, and if the center pin on the switch is already tinned, all you have to do is melt some solder and get a little solder on each of the other two to melt, and you're good. You're home free. Okay, now we reposition that common so it's that common conductor is now sitting pressing tight against the center pin of the next switch. So we solder that one. Notice that this one, though, that the common is passing below it, not above it. We don't want to solder it there, plus you see the air gap. Okay, so we basically just kept manipulating this conductor to the top side of those lugs until we got down to the end, and now they're all soldered. This little section right here we're going to remove later. Or actually it's at the other end. Okay, so here's our finished common. Our common plus wire complete. Now we're going to need some conductors. This is typically the cable that I use, although I don't use it as a cable. I use it as a source of multicolored conductors. Now I just noticed something. If you look down at the base of the red wire and the yellow wire where it meets the vinyl gray sheath, you'll see little nicks in them. That's not a good idea. Now that little bit's not going to hurt. They're not going to short together on anything, but you need to be really careful when you pull that insulation back that you don't nick the insulation on the individual wires. So here we have yellow, orange, white, green, blue, and brown. We would normally use those 6 for the 6 toggle switches. And of course the red and the black we can use for positive and negative wires somewhere else in the project. Okay, so first thing we're going to do on these 6 conductors, yellow, orange, white, green, blue, brown, we're going to strip back about 1/4, maybe 5/16 at the most of an inch. We're going to make sure that the conductors are twisted together, and then we're going to tin them. So if you look close, you can see some solder has been sweated, wicked into that copper strands. Here I'm showing you that you needed to strip back the conductor for whatever length of conductors you need. I guess you would have known that. Instinctively, you had to get rid of the gray plastic sheath in order to use the individual conductors. But this is what it looks like. And there's actually a tool that makes this real easy. If you're going to use your wire strippers, remember the wire stripper doesn't have a hole big enough to do this. So you're going to have to close the wire strippers down on the gray vinyl tubing and then kind of rotate the tubing inside the teeth on the strippers just enough to cut into the surface. Then you can take and twist the conductor at that point and it should break through the rest of the distance. And you're going to have to pull off that gray plastic sheath. Sometimes that's very difficult to do, so you might have to do it in sections. But you're going to discard, you're going to throw away that orange fiber that's used to strengthen the cable and the aluminum foil shield. There's also a drain wire. So if you look down at the bottom of this drawing, down there you'll see some shiny conductors coming out. It actually continues over underneath the yellow. That's a drain wire. That's in contact with that blue aluminum surface, so any electromagnetic interference that's induced in that foil will be drained away by using that ground wire. Well, we're not using the shield or the drain wire anyway. We just wanted the 8 conductors. Okay, so we tinned the blue one. Now as we stripped it back, you're going to set your box with the switches closer to the table. In other words, when we solder the common that you see there already soldered, it's now on the bottom of the tab. Remember before it was on the top, because we want the maximum separation between that center lug and all the soldered joints and that upper lug, just for the sake of avoiding a short. So what you do is you take that tinned wire, as you see there, the blue one, you put it through the hole just enough so that when you let go of that wire, it relaxes and it stays in there because the weight of the wire keeps it in that position. This may take some practice. Do not get in a hurry. If it falls out when you go to start, just take your time. Okay, here you see it's soldered in there. That's not a perfect solder joint, but that's definitely good enough. But look at the clearance between the center pin and the pin that the blue wire is soldered to. That's why you want that common on the bottom, or you want it away from the side of the switch that you're going to use. Now remember, if you're using single pole, single throw toggles, you've only got 2 pins, but you're still going to solder the common on the far side from the other pin of the switch. Toggle switch is complete, except we're going to remove this short piece later. Not right now, though. We want it there to hold everything together. I realize this is a blurry picture. It's too late to go back and take it over because it's all put together. But you can see here that we had the solder tabs on those switches on the top side. That way when we rested the blue, green, yellow, orange, brown, and white wires in there, gravity basically held them in there, kind of wedged in the hole. Now, I didn't put all 6 of these in there, then solder them. You should put the first one in this case it was the blue one, solder it, make sure it's good, then the green one, solder, make sure it's good, and so forth. Now, remember that you mounted these switches from the outside of the box with the nuts on the inside. So remove the nuts from the switches on the inside. Now, one thing I want to point out, you drilled these holes and you didn't drill them perfect. No one does. However, these switches are now connected together rigidly by that common conductor on the back. You're going to pull these out, but when you go to reinstall them later, you want to hold them in this position and then just flip them over to the inside and the alignment should be perfect. Okay, so go ahead and slide the assembly out carefully so as not to bend your common conductor. Later we'll flip the assembly over and insert inside the box like I just mentioned. So I did that for you here, even though we're not going to do this yet. So I just show you that you just flip it over. You see where the red conductor's at? It's to the right, and it's to the right there. But for now, we're going to lay this aside. So I usually just roll the wires together and lay it off to one side. The last time I did this, I built 6 of these trainers at one time. So I actually built 6 of these assemblies and set them aside, and then everything I'm going to show you, except these were the ones that I shipped from the PLC Professor website as a product. So it's not going to have the lights and a wiring diagram. Well, we're going to stop right here. So that concludes Part 2a, maxing out the little box. Thank you for watching. Look for Part 2b.